Please, go ahead, Jari.
So everybody can hear me, yeah. So my name is Jari Saarinen. I'm a CEO in a company called GIM. And I don't know, I'm not really that aware of the artificial intelligence, so to say. And I think one of the key tasks for AIHelsinki, if it expands, is to organize a sauna evening and explain what all that we do is artificial intelligence and what not. Anyway, we do robots. I'm gonna talk a little bit about our company. I assume that not many of you know us that well. We started 2014 in the beginning, so it's about 2.5 years now, and we are Aalto University spin-off. Basically, the whole founding team is or has been a very long time researchers in automations and systems technology, and the main focus of the research group that I've been working with has been intelligent mobile machines. Our kind of last big thing what we did in the academia was that we had this Center of Excellence in Generic Intelligent Machines. This is a status granted by Finnish Academy, and it was a kind of a big thing to get it purely on applied science, hardcore technology group. When we started the company, or before we started the company, the kind of the political situation and the expectations for robotics started to grow up. So more and more talk about bringing robots into everyday life started to emerge. We also all seen, if we have ever been listening to any robotic talks, we have seen those forecasts, how the service robotics is going to be multi-billion business opportunity, and it's like the biggest hockey stick that there is at the moment. And we do believe that robotics will be the next big thing, that the big technological breakthrough that will influence all of us. It's just a matter of time. Well, actually, we see it already, not maybe influencing so much, but more and more applications are emerging. And one of the reasons for this is that actually the technology for building mobile robot applications is getting more and more mature, meaning that we get better sensing technology, we get much more computational power, and with variety of different kind of technologies, which all come at cheaper price all the time. So this all is pushing the robotics into state that the actual applications can be done. All right, that's about the birth of the company. Then what's the generic intelligent machines? So already in the research institute, the kind of the core idea was to do surgery of a robot. So robots are systems, such as any other technological systems. The thing with robots is that they do differ a lot from application to application. But there are technologies which are generic enough so that you can use it in many different applications. And this is also something that we as a company are pushing forward. So we try to develop kind of, let's call it an automation black box, where we can attach different kind of sensing technologies, use different kind of approaches for different kind of applications, so that all these great ideas that people have, that could you do this with the robot, can be done. And basically, our goal is to develop such a platform that we can sell this platform for other system integrators. Just a brief introduction to what we do at the moment. So one of the customer projects that we have is at the moment is security robots. This is basically developed for Chinese markets. So we are developing a physical system which is patrolling outside of the neighborhoods, reporting if there is any suspicious activities. In this project, basically the GIM is again, doing the kind of the autonomy part. So we do the outdoor navigation and we do the people detection, and then other partners do some other stuff. Not really robotics, but still perception technology. So this kind of technology can be applied in many contexts. This is a device which is going to be the next generation measurement device for the fitness centers. At least in the first case, it's a fitness centers. The device is basically, it makes a full body 3D scan of you. And then we have done plenty of algorithms which are calculating how your body is, what are the measurements of your body, what's the fat percentage of your body, what's the metabolic age of your body, and so forth. And then already mentioned, we actually have a live demo or live system in Design Museum. The big grand idea behind this was that, well, museums are dull. What can we do about it? So let's make the whole exhibition alive. And this was the starting point of this project. We developed, actually in 3 months, we designed, developed, and did a small-scale manufacturing of 8 of these robots, and 6 of them are now in the Design Museum. They carry the furniture around there. You can go and stand in the middle, and the whole space is moving around you. It's great. And then from, let's say, algorithmic side, mobile mapping is something that is very mature at the moment. You can find very expensive laser scanning systems that are doing this, but actually our algorithms can cope in situations where it is possible to just drive through some areas and collect the data and make the maps. And there's a number of applications for this kind of technology. All right, so I didn't actually know what's the level of sophistication of the audience today, so at least the first presentation was very sophisticated, but I hope you find something interesting in this. When we talk about robots, especially public, there's a lot of expectations, there's a lot of fears even. What is the robot? What does it do? Where's the intelligent, and when does it kill me? I'm taking just an example here from this Design Museum robot. I'm gonna show you some industrial secrets, how it is built. But first, let's just look the video. So we see a little bit, get the idea of what's the purpose, how they work. So in fact, for me, a robot is something that it has to have some actuation, it has to move. If it's a mobile robot, it has to move. It has to have some level of perception, and it has to have some control software which is actually influencing the behavior of the robot. Once it sees something, it does something. And while this is super simple application, this is basically a replica of the vacuum cleaner robots, the first vacuum cleaner robots that you received from the market. It's just, if you would put a vacuum cleaner in it, it would do the job just as well. All right, so what we actually saw here was in the video, these 3 slides. So these are something that you find from each and every robot. So you have to have the actuation. So here we have a DC motor, and basically when you have 2 DC motors, that's enough degrees of freedom so that you can control the robot on a flat floor to go anywhere. In this case, of course, we had to do some sensing, and one of the sensing technologies implemented in this was just plain magnetic sensing. This is to put the virtual walls into the exhibition space, that the robots are not going anywhere, but they stay within the boundaries that we define. Then we need energy. Every mobile robot is dependent on energy, and this is one of the big bottlenecks of robotic applications. You see very fancy humanoids. They do great stuff, but they don't actually do it very long. So after 15 minutes, Asimo is dead. What's the use of that robot? You need some computational power, and in fact, in this case, we had very easy user interface. So basically, you just switch it on and it goes. And then you need some level of perception. In this case, we are using a 360 laser scanner, which is measuring up to 6 meters. We can see if people are approaching the robot. We can see if the robots are approaching the wall, and we can do the decisions based on that. Very simple. So if we then go into different looking robots, nothing really changes how the robot is built. It's still the same. You have the motors, you need the energy, you put the computer on, and you start controlling them. What actually changes a bit is then how you define the task. So in this case, our task was really, in the design museum case, the task was really simple. Stay in an area and move. That's pretty simple definition. If we want to do something more clever, then we need something extra. Now is the time for next video. So this platform is actually something that we are not really selling at the moment, but it's more of a development platform that we did. Sorry, where do I silence it? In this case, the purpose of this device has been that we actually build a block, which is the electric work machine block. It demonstrates the systems that are needed in every single electric machine. If you go into a car manufacturer and you start ripping the car, you find the same components as are in this one. Then we have developed this, as I said, the navigation system, which allows it to move in different conditions, outdoors, indoors, and yeah. And then hopefully someday it's doing something useful even. So now if we take a look at the subsystems that we find apart from the mechanics from that one. So basically there is something called mapping and localization. And now the positioning is actually something that is really important for autonomous applications. Pretty much any automation system needs a frame of reference. If it's a mobile, then you need to be able to address the points which you want the robot to go, where it does, what it does. Traversability, in a sense, means that when you are working in a human environment, everything changes, so you cannot just make a map and assume that everything stays the same. But instead, from the perception, you need to find out what is the areas that you can put the robot into, or the robot has to figure that out itself. Planning is something where, let's say, traditional artificial intelligence has been. This is actually the part that I understand this artificial intelligence. So it's basically a kind of a search algorithms which are leading into shortest route, safest route, or something like this. Then, of course, once you have established frame of reference and you have planned a trajectory through the environment, then you need to be able to control the robot through it. And while you are doing it, you need some real-time perception, real-time decision-making, which actually makes sure that the robot is not colliding with anything. All right. So how the robot sees the world, of course, depends on the sensor modalities. One of the problems of establishing these frame of references has been that how do I express, how do I represent the working environment where the robot is moving efficiently so that we still allow real-time operations. And for this, we are using a kind of probabilistic approach which models the environment as a set of normal distributions. And this actually allows relatively compact representation in a sense that large surfaces can be represented with just a few parameters, which then again greatly reduces the computational requirements that the robot needs. So what happens here is that a robot is mounted with a 3D laser is just driving through the environment. Every time, in 10 times per second, it gets a measurement of the environment. This is like 700,000 3D points. So you can imagine shooting with the laser beam and then taking 700,000 of those laser beams, and the endpoints of those laser beams are the things that come into the robot. Next, you put this into the representation, and then you start accumulating this information so that you get a complete picture of the environment. Now, the first section of the video was a large factory. It was about 200 by 200 factory. This is actually then taken from the car, so this is kind of a city block data. So the robot is, or actually in this case, car is driving through the city block, and then continuously it's mapping while it's going. And this is basically the way that we see that we can establish this frame of reference. So we do mapping once, and then we start using this map to define the tasks, what the robot needs to do in this environment. All right. So where's the artificial intelligence? Anybody has ideas? No? Well, learning this representation is machine learning, isn't it? There's a specialist in machine learning. Yes or no? It is, in a way. There's also different things that you can learn. You can learn about what happens in a specific space if you observe it through the time. There are different models to do that. Mostly at the moment, where we use machine learning, I can actually show you the video again. Much easier than me explaining anything. So this is basically the task that actually also many machine learning guys, and I guess machine learning is artificial intelligence, many machine learning guys are now solving. So how to get from different sensor streams the relevant information of the environment. What we see in this picture is a combination of 3D laser data and cameras. And basically from cameras we use shallow learning methods, so to say, because deep learning is very, very hype at the moment. Shallow learning methods to distinguish different features. And now, for example, humans are very interesting in the environment, not only because we are doing a security robot, but because also humans are something that we should be able to avoid hitting. Walls, cars are not so serious, but people are serious. And in this case, we combine basically the 3D sensor information we can get from the 3D data. We can actually extract the background, so while the robot moves, we can, through this registration process, which is part of the mapping, we can get the points which are not actually fitting into the stationary world model. And when they are not fitting in the stationary world model, we take those points, and those are our candidates for dynamic points. And dynamic points are bad because they are moving and they are potentially dangerous for the robot. So once we get these points, we put those into cluster. We have some features, machine learning features, which we are teaching even for those points, and those give us one candidate. We also then take from these clusters, you saw these boxes. So we take those candidates and only use that amount of information which we push to image-based machine learning algorithms. And these give us another result. Now hopefully one day this combination of these is strong enough so that we can say that, okay, it's 100% certain that no human can go under our robot and get injured. And then this is my picture of the artificial intelligence. So basically, when we are doing the kind of planning, it's about finding options in the future, so to say. In every time step, the robot has limited amount of decisions to make. So each of these decisions are based on, for example, the controls that you can give for the robot. And then each of these will move the robot in the future. And each of these will again have decisions. And when you go further away, you have really a huge amount of, you have a big tree of possibilities where the robot can end up. And then the task is to find the best of these possibilities that suits in the situation. That's my talk today.